Hello, everybody, and thank you, Sabina and Niraj, for arranging this. I'm happy to talk at these seminars. Today I'll discuss a little bit the general area of learning from limited labels and from unlabeled data, with focus on perhaps a little bit more on the few-shot learning setting. I'll be kind of pointing a little bit to the fact that perhaps we're not making much progress in those directions. So without further ado, maybe for those of you that are not familiar with the subject, so what is learning from few labels or few shot learning? So probably most of you are familiar with the fact that deep networks today are dominating learning and dominating computer vision. Of course, I will be using computer vision examples, for instance, image classification, image segmentation as running examples during the talks, but of course the concepts are applicable in other areas as well. But you're probably familiar, those are by now popular subjects, perhaps after 10 or around 10 years of a learning boom in vision problems and in NLP problems and so on and so forth. So few-shot learning, assume that you have some kind of training on a set of classes, supervised training, and then you observe what you see here, and then you observe a new set of classes for which you have just a few examples. You don't have many data, 5, 10 examples that have labels, and you want your model to generalize well on unseen or unlabeled point, to classify well in these points in these classes without having to train from large numbers of images, as is typically required by modern ML models. So this is pretty much, I would say, this along with other problems, it is pretty much obvious the gap between human and machines. So for human, you wouldn't need to look at 1,000 cat to recognize a cat. It's basically, even if you have never met a cat, show you a cat, then the next cat you would recognize it's a cat. So this is pretty much one-shot learning setting. And modern models, they have difficulty into learning from few examples. So there is this gap, pretty much like the gap in adversarial robustness, where humans are very robust to small perturbation, where our ML models are not robust, and so on and so forth. So the problem in itself is interesting scientifically, at least to understand this gap, and perhaps, at least in my opinion, the difference might lie in the fact that humans use a lot prior knowledge about their context and about the setting. And this is perhaps where the gap lies. Essentially, we're not data-hungry machines that memorize data. We are more than that. So that's the general setting. And this is what perhaps motivated. So this is a subfield, I would say, of learning with limited supervision, or also from unlabeled data. And it's quite large sub-community, I would say, in the field that work on this specific setting. Why is it interesting? I would say perhaps, at least from what I've heard from people here and there in the community, there are probably two opinions. Some people would argue that why would we care about learning with limited labels or from labeled data? At the end of the day, we will perhaps just end up having tons of labeled data, and that's it. All we need is supervised learning. And there is also, on the other hand, a big chunk of the community working on these subjects. They are very popular, and even on supervised learning, and arguing basically that unlabeled data is the key to strong machine learning and toward generalization. We have to make use of it, and hence the popularity recently of unsupervised learning and of contrastive learning and so on and so forth. So few-shot learning or learning with limited annotation is bit in between, where we try to use few labeled data points and a lot of unlabeled data if you can. Why is it interesting? Okay, let's take, for instance, other tasks beyond image classification. If you think of semantic segmentation, for instance, it's a very popular task and very useful. One applications that come into mind right away is autonomous driving. So what you can see here on the left-hand side is an image from Cityscape, which has been annotated. So Cityscape is probably one of the most popular data sets for semantic segmentation. It's 5K images taken into Zurich from a car, basically. And sorry, perhaps at average, one image would take 1.5 hours by a human to annotate, to label pixel by pixel. So it's a dense prediction task, much more complex than image classification, for instance. By the way, feel free to interrupt me at any time. We can make it interactive during the presentation. I don't mind about that. So of course, you label 5K images in Zurich, and then you might come to Montreal or Edmonton in a snow day, and then your model is horrible and at testing time, because the setting changed completely. I will talk a little bit more about this. So you have to label again, so if we take this specific task, for instance, semantic segmentation. So popular data sets are pretty much confined to subset of the real world. Let's say here it's urban scene. It's not seen, for example, indoor scenes. With less than 30 classes that you typically see in urban scenes. But the world is millions of classes, and we cannot label everywhere. So if you train your model on cityscapes and then you go to objects like daily objects or food, then your performance will drop a lot. So I would side with maybe people that say we need unlabeled data to go to stronger machine learning model, because I think we cannot label everywhere. And perhaps we would have done it by now during these 10 years, I would say, of spring of AI. We would have done it if it's doable with all the resources, with all the interests. So in my opinion, it's not doable. And in my opinion, it's like saying, oh, well, we will have unlimited resources at some point. Why do gradient descent and investigate optimization? We can just do exhaustive search. So it's a bit like this when we say we will label everything, in my opinion. So this is why it is interesting. I think leveraging unlabeled data is important at the end of the day.
That's a quick question.
Yeah.
You talk about labeling. There's sort of two ways you can talk about different subparts. Are you talking about labeling a person, or labeling a hand and a foot or a person? Or does that something that will be domain specific and people will give? I see on the far left, you list person, rider, car, and so forth.
Yeah. So I guess this depends on the task of interest. So your semantic labels could be a person or could be parts of person if you are interested in part of persons. And this even makes things further more difficult because it's task dependent, right? So here in this specific data sets, given that the end application is perhaps autonomous driving, nobody was interested in labeling hands and legs. But of course, these are also relevant tasks, right?
So the other way you could have part of or subset would be you have person, you have man, woman, you have child.
Yes.
I guess for a driving vehicle, I guess it may not make that much difference. But again, it's another dimension. And as you talk about different sets of classes, I can imagine identifying a cat would be relatively easy, but distinguishing different breeds of cats would be more complicated.
Yes. Yes, I think at the end of the talk, I will talk about few-shot classification, and there are different data sets like CUP, for instance, where you have types of birds. So it's fine-grained classifications, and indeed, this might be more difficult. Yes. Yes, but this actually goes in favor of the arguments of we cannot label everywhere.
Okay.
Yeah.
Thank you.
Yeah. Okay. So and let me broadly define the subject of having limited labels and using unlabeled data. And few-shot learning is not completely different, the setting, from the standard semi-supervised learning setting, where you have few data points that are labeled and the rest, perhaps much larger set of points that is unlabeled. And then you try to learn from both, like what you see here, for example, in the context of semantic segmentation. So what you see here is full supervision, where you label every pixel in the image. And here you see a semi-supervised setting where you label just a few pixels. And this is pretty much another motivation. So labels, perhaps we've observed huge progress in natural images in the last 10 years. And perhaps because the labels could be obtained in a much easier way than other fields. So labels are not only expensive in some fields, but they might need expert knowledge, right? So you could not do this, for example, and crowdsource the labeling of medical images. If you are not a medical doctor or even a specialist, then I show you this image, it tells you nothing. You cannot label it. And this actually, if you look at the data sets in medical imaging, except maybe few in X-rays and classification, if you look at segmentation data sets, we are not anywhere close to the 5K images of Cityscape. And that explains it. In fact, the typical segmentation data sets that are public are maybe 40, 50 subjects, 100 subjects for the big ones that are segmented. And in part because you need very specialized expertise, and also it's done 3D annotations, takes several hours of not just any person time, of radiologist time. And maybe the last part is domain shifts that make things worse, because essentially, if assume, for example, you training data from one clinical site, and then you go in another clinical sites where the population change, the MRI, the acquisition protocol change. So assume, for example, your source data, which has labels, let's say you did the effort and motivated radiologists whose time is very busy to segment 40 subjects, those blue ones in your source domain, and then you go to another hospital with a different MRI acquisition protocol, and then you apply to a new data, which kind of has some differences, in appearances, in many aspects due to changing protocols or in population. If you project the images, say, on some kind of 2D space, then you would see some kind of domain shift, like what you would see here. And then you might observe that your performance drop a lot, right? So you need to label again, basically. And this makes things worse because we could not label everywhere at the end of the day. This is an example also across modalities where, for instance, you have labeled MRI data, and then you try to apply to the same tasks, which is hard here, but it's a CT, and you don't have labels for the CT. So this typical setting is technically called unsupervised domain adaptation, or UDA, but it's highly related to semi-supervised learning as well. So you try to learn from labeled data in one source domain and unlabeled data in the target domain. And of course, if you just train on the source domain and there is a big domain shift, then of course you would observe some big decrease in performance as opposed to training from similar data. So you'd have bad generalization. So this is all about generalization as well. And beyond medical imaging, there is still a lot of interesting vision where people try to train, let's say, on autonomous driving scenes in one city and then try to generalize in another city where you don't have labels, for example, in semantic segmentation. So in a nutshell, domain shifts are everywhere, but we cannot label everywhere. So these are examples, for instance, and there is fairly big literature in every of these subfields, SSL, UDA, or few-shot learning. They are essentially tackling very related problems. So here again, another example, you have cityscape and Zurich, and then you apply your data on autonomous driving scenes in Frankfurt, and then you would run into trouble, or again in Montreal or in Shanghai, and then performance drop by significant margins, indeed. Okay. So I would say technically unsupervised domain adaptation, where you use your source data that is labeled and unlabeled data in the target domain, is some kind of semi-supervised learning, but with domain shift. So you can think of it as a learning problem that has this form, where you have data labeled in one domain and data that is unlabeled in the other domain. Whereas semi-supervised learning, the underlying assumption is that they both come from the same domain, labeled and unlabeled data. But technically, it is pretty much the same problems. So let me just take this. Okay, yeah, few words in these slides. I don't like it much. Of course, I don't like reading them. But just it's a summary slide, basically. Okay. Few-shot learning is very popular. You would probably have hundreds of papers now every year. Same for semi-supervised learning, same for unsupervised domain adaptation. But in a nutshell, what these methods are doing are pretty much leveraging unlabeled data with some priors. Okay, and perhaps here I give a quick summary. You could use priors on the structure of unlabeled data. I will discuss some in the next slides. You could use perhaps priors, if you're dealing with medical images, you could use priors that come from anatomical constraints. You could use invariance priors, when you apply rotations to images, that's the same class, for instance. And this is pretty much the principle. The invariance principle is what drives contrastive learning in supervised learning, which is becoming very popular nowadays. You could use multimodal priors. You can assume that your images are associated with some text data, and this text can give you good priors to learn. So in a nutshell, in my opinion, it mimics better the human approach, where humans are biased by prior that depends on the context, by the way. Text also information is associated with medical images, for example, radiology report and so on and so forth. So all this, in my opinion, is interesting. And we have a lot of work to do ahead, in my opinion. So I will just take two examples of structural priors, which are very classical in learning. I mean, there is nothing completely new here, and surprisingly, they are very competitive in an abundant literature in few-shot learning, recent literature in few-shot learning. So I will start with a very simple type of regularization that is very intuitive, and probably many of you know about it already. Any questions so far about? Good. Okay. So let's say a general setting where you would want to learn from both labeled points, data points. They could be images, they could be pixels, and unlabeled data points. So what you see here on the left-hand side is some kind of, imagine you have just one labeled point per class. And so you have many possible decision boundary. One of them is this. And now imagine that you have unlabeled data on top of this, and that would guide you maybe toward a more meaningful decision boundary. So this is perhaps a general setting. And this is maybe, let me start to try to introduce notation a little bit that will be running throughout the next slides. But let's say, you have some classifier or some embedding. F theta p, p is point, theta is the parameters of your classifier. You have some labels, some simplex vectors, binary vectors, example yp for each pixel. So those are your labeling. This is some supervised loss in a sense. And then for a labeled point, you have some kind of pairwise function, which depends on the classifier or the classifier embedding on pair of point Q and Q, and some potential which depends on two pairs of points. So what is the generally what is the objective or what is the purpose of this pairwise function is very intuitive. It's a structural prior. So basically, we want to tell the classifier, look, for points that are very close in the feature space or in the input space, for example, these 2 points measured by WPQ, we don't want the decision boundary to go through and separate them into 2 different classes because they are very close in the feature space. So we want the decision boundary to basically go through low density area in the feature space. Okay, we don't want to cross high density area. So you can encode this in some function, some pairwise function that penalize or make you pay huge penalties since you are minimizing the loss when you make 2 points that are near each other separated into different classes. Okay, very simple. So assume you have some classifier, let's say deep networks. F theta could be P12C could be just your probability outputs of the network or some embedding. YP again are your labels, and then this is one very typical example of structure regularization that you could use. So assume WPQ measure how close your inputs points. So it's a fixed potential. And then you're basically telling the model, okay, if you don't give the same predictions to 2 points that are very close, so WPQ is high, then you would pay a high penalty and you're minimizing. So the model will just encourage points that are very close to each other, like here, these 2 points, to be in the same class. That's basically what it is. Very simple. And there is nothing new in this. This is very popular in semi-supervised learning, far before the deep learning era in SVM, for example, or Gaussian fields and harmonics and so on and so forth. So it's just a few examples. Perhaps the first deep learning work using Laplacian regularization was more than 10 years ago. So there is nothing really completely new here. And this is an example. This is an example of use which will show you that this is actually interesting. You could do something with this that is quite useful. So think about semantic segmentation setting. So this is from this example is from this work that we had in ACCV back in 2018. So think of a semi-supervision setting where you have few scribbles or few pixels that are labeled, and the rest of the pixels are not labeled. And here, actually, this is interesting because Laplacian regularization is known in clustering, in semi-supervised learning. But if you think of these probability or softmax output as binary variables, this becomes exactly something very popular in computer vision. It's called conditional random fields on the POT model, which actually embed perceptual prior on your segmentation. Like you want the boundary to be aligned with edges with differences in color. You want them to be smooth. So these perceptual prior are even consistent with the human perception. Like we prefer smooth boundary. We prefer boundary that are aligned with edges. So if you choose WPQ, this pairwise potential, just to be, related to the difference between colors, you're basically telling the model, okay, you don't have labels for all these pixels, but I'm telling you something. Pixels that are close in color, that are close in space, you should consider putting them in the same class, basically. So this is a perceptual prior, in a sense. It will try also to align with the edges where there are different colors. So this is essentially an unsupervised loss which use color information to try to drive the solution. Okay. And this is actually pretty cool. So if you look at the, well, this is just the size of scribble, but if you look at the just training from the labeled points, the scribbles here, this is the performance that you see in intersection over union. And basically it brings you that just this Laplacian regularizer, it brings you 8% up and close to full supervision. Maybe 2 points below full supervision, and this is with just 3% of the labels. So the scribbles here are just 3% of the labels. So you can do things with priors that you can put as unsupervised loss terms. So just 3% of the labels, you get 97% of full supervision performance in this specific setting of semantic segmentation. So any question here before I move to a use case of Laplacian regularization By the way, Laplacian regularization is very famous too in classical clustering methods, such as spectral clustering, although very different technically, but it's the same principle. You pretty much, you put pairs of points together in the same cluster or class when they are close to each other in the input space. Okay. So any questions before I go to a few-shot setting, few-shot image classification setting, with this recent work that we published last year in ICML? Okay. So let me just look a little bit and zoom a little bit on few-shot learning, because it's a very popular subject. There are a lot of works, and I was personally surprised by the performance we had and other team had in the recent years with very simple baseline, given the amount of work that has been done in this subfield, many of which is quite convoluted and quite complex. So if you look at the literature in this area, so a large body of recent works are mostly based on what we call meta learning. So I'm not gonna do an introduction of the subject, and I'm by far not an expert in meta learning, but I will just go quickly through the intuition behind it, or learning to learn paradigm. So assume that, okay, let's go back to the few-shot setting. So you have data that is labeled with a set of classes that we call base classes, and you have at testing time, you have few-shot tasks, okay, where you have few samples, let's say 1 or 2 per class that are labeled, 1 for 1 shot, 5 for 5 shots, and then you want to predict for a set of points for the task. And those new classes are different from the base classes, okay? So let's say you train an embedding in those base data, F theta. So in a nutshell, the learning to learn setting try to mimic the challenges that you would encounter in testing. So it basically try to create artificial episodes, which are artificial tasks during training, not during testing, and try to do episodic training. So basically divide the base data into small tasks and assume that the labels of few samples are not available, although we know them, and then try to train in a way that minimize the error on those labels. So it try to mimic the setting of the testing time, and this is why we call it learning to learn paradigm. Of course, it will introduce a lot of hyperparameters that are related to the choice of these episodes, and it would somehow implicitly assume that you would encounter this setting in testing. If you choose episodes that are, say, 5 shot, then you are kind of assuming that in testing you have 5 samples that are labeled. So this is in a nutshell how it's like the general principle, and the amount of works in the settings are quite substantial and impressive, I would say, in the recent years for few-shot classification and even for few-shot segmentations or other tasks in computer vision. So taking a few steps backwards, not just our team, but few other teams in the community realized that actually some simple baselines and good regularizers, those we know from or used from a while ago, outperform very complex meta-learning approaches. So I'm listing a few papers here. I will discuss very quickly these 2 papers. But this is pretty much it, and those works are pretty much based on simple regularizers, for example, Shannon entropy or Laplacian regularization, or recently also the mutual information. I will discuss a little bit about it very quickly in the next slides. So no meta training. We just do some very simple conventional training based on cross entropy. And let me just very quickly here discuss 2 types of inferences for during testing time. So you have a few short tasks. So you have a few samples that are labeled. We call them support samples. Okay. For example, you have 5 classes. We call this 5-way. And for each class, you have 5 labeled samples. So 5-way, 5 shot. And then you have a number n of unlabeled images for which you want to predict. So there are 2 settings. So in the inductive inference setting, you predict for these unlabeled points one at the time, okay? And in the transductive setting, you would predict for everybody at the same time. You assume that you have access to all of them at the same time, okay? So the transductive setting basically predict for all test points instead of one at the time, okay? And of course, here, the transductive setting does not assume that it has access to more training data or more unlabeled data than the inductive setting. We just predict for many points at the same time, as opposed to one point at the time. And an ideal or example for application of transductive setting is image segmentation, where you have access to all the pixels of a test image at the time. You can think of this as a transductive setting, because naturally you will have access to all the pixel at one time. And I will discuss specifically one example at the end of the talk, okay? So let me focus on the transductive setting, and what we are doing here is very simple. It's some kind of Laplacian regularization, similar to what you would do in clustering algorithms. So we have just some variables, assignment variable YQP on those query points for which we want to predict labels. So these are just binary variables, okay, YQC. And we have two terms, okay? XQ is just the feature embedding that we have trained on the base classes applied to these query points of the task. So we treat each task independently of the other tasks. MC is the mean of support sample. So this is some kind of supervision, okay? And this is essentially, this term is very simple. It's just basically, if you remove the Laplacian regularization, you just label points using their nearest support prototype. Basically, it gives them the same label as the nearest labeled point. So this is some kind of nearest neighbor. In fact, it's very simple. And of course, we don't use it alone. And then we have a Laplacian term, which is basically this term. You try to encourage nearby point to have similar sign, and we optimize everything with respect to y, which is the assignment of data points. So the optimization itself is interesting. I wouldn't have time to go into optimization details. We have specific choices to make it fast, and it could be implemented in parallel. So it has so the inference time is very close to inductive inference time, indeed, in our case. And this is pretty much what we do. We optimize this objective at inference. We call LaplacianShot for each task. So I wouldn't go further into details, but well, details are in the paper. But this gives you an idea, pretty much. So on some standard benchmarks like mini-ImageNet, for instance, with the Laplacian-Shot, you would be I think there are methods that followed up, I guess, after last year publication of this work. It's probably not the first now, not even the fourth or the fifth, but at that time it was a pretty much good margin compared to the best performing methods across different networks, across different data sets, both the transductive and inductive settings, perhaps even 4 or 5% compared to the best performing method. The same on Untitled ImageNet. So details are in the paper if you are interested. Well, of course, there is the choice of lambda, which is important too. That's the trade-off parameter between these two terms for each task. And interestingly, when we try to get the lambda on validation data, which has different set of classes completely, it seems that the best lambda correspond also to those obtained on testing. So it's possible to get the best lambda from validation data. That's good. Again, I would not be able to discuss optimization aspects, which are interesting by themselves, but the transductive runtime per task is pretty much similar to inductive methods.
So can I ask a question here?
Yeah.
So what is the difference between the 1-shot and 5-shot in your table?
So the 1-shot assume that you have, for each new class, you have one example that is labeled. Okay. The 5-shot you have 5 examples that are.
Oh, so it refers to the number of times.
So it's more supervision. Okay.
Okay, right. Thank you.
All right. So takes away. I guess I'm not gonna read these lines, but pretty much constrained graph clustering. There is we were not even training again or fine tuning the network. Works very well. You can put it on any model, in fact, and it's quite fast. So I invite you, if you're interested, to take a look at the paper and maybe run it. I will give the links to the code later. So if there are no questions, I will talk about another regularizer to finish the talk, and perhaps with focus on a different application, and also connect it quickly to something very well known in information theory, the mutual information. Okay.
Sorry. Do you have like unlabeled data in that previous setting, that last setting? So where does that unlabeled data come from?
So the unlabeled data are those test points for which we are predicting the labels.
Oh, okay. Nice. Yeah.
So but we are not retraining. We are just predicting the label for all the points at the same time. So it's implicitly it's using the statistics of all the points. Okay.
Right. That's why it's choosing selective.
Yeah. So of course we are not the only method that is transductive. So transductive methods, there are a lot also in the literature. Many of these are transductive also. So there are both transductive and inductive settings. Okay. So entropy or Shannon entropy minimization is also something very popular in semi-supervised learning a long time ago, actually, and even in clustering, in discriminative clustering. So there is nothing new or modern about it, and the principle is very simple. Suppose that you have labeled data points, so you have a cross entropy over them. With S theta, PC, or the softmax predictions. And on unlabeled data points, you would have the Shannon entropy. This is exactly the Shannon entropy, because you can think of these as probabilities, the output of the network. And very intuitively, you can think of it as some unsupervised cross entropy. So look carefully. If you change this softmax prediction by a label here, but you don't know the label on unlabeled data points, then you have exactly the expression of a cross entropy. Okay, well, this looks abstract. Why this would be useful on unlabeled data points? So let's try to take a look what happens with this. So first of all, I'm just plotting here, I'm just plotting the Shannon entropy for just two classes. Okay, so this is how it looks like. So here is the softmax prediction, is the probability, and this is the Shannon entropy. It looks like this. So basically, push the softmax predictions to 0 and 1 when you minimize it. So it makes the predictions confident, pretty much like cross entropy does also in the supervised learning case. So this may not look very convincing to you. So this is what it tried to do in the, let's say, for the learned embedding, and this is why it's a structural prior. So intuitively, this corresponds to a high entropy, where you have a lot of points that are not confident, where the prediction is pretty much close to 0.5 here in the case of two classes. And this corresponds to low entropy, where the predictions are confident. So again, perhaps intuitively in a way similar to Laplacian regularization, entropy tried to have decision boundary in low density area. And again, this is something called as or known as the cluster assumption. So it's a structural prior. It prefers learning representations that are quite disentangled in terms of classes. This is a real example for image classification, where adding an entropy term yield a better separation of the data here in this example, for instance. So it increases the margin between the classes. So it should be interesting and useful as a structural prior to leverage your unlabeled data. Okay, this is another example from unsupervised domain adaptation, where show you here basically a model trained on your source data, and then when you apply the model without adaptation to an image, and then adding entropy minimization, basically make your prediction very confident and crisp, and segmentation much better if you look here, for instance. So Okay, this is good. Entropy minimization is good. But let me discuss a little bit why it should be used with care. Okay, so we should use it carefully because it might lead to trivial solution. So think of a two-class problem. You have a softmax here for one class and one minus softmax for the other class. So these are the probability output of your network. So this is a good solution if they are, the prediction are 1 here and 0 here or vice versa. So you're in these parts. So you're minimizing entropy, right? But this bad solution where all of them are 1 is minimizing entropy too. But you don't want this type of solution. You don't want this type of imbalanced solution. So minimizing entropy on its own might lead to a trivial solution where all the points are predicted for the same class in some sense. So if you consider, so this is a way to correct it, and I will connect this very quickly to the mutual information between the learned features and the predicted labels. So if you think of the marginal probability of the labels, if you sum over all the softmax for one class, so this is the label marginal, in fact. And then if you try to maximize the entropy of those label marginals, that is going here. The maximum is achieved when every class pretty much have the same proportion. So this would avoid the trivial solutions of the entropy. And interestingly, if you take the entropy and you minimize the entropy and then you maximize the label marginal, which is what would give you something like this, then both of them together are actually nothing else but the mutual, an approximation of the mutual information between feature points and their latent labels. In fact, this is interesting. And this is also used a while ago, even in Bayes clustering. Okay. So this is some kind of mutual information. And of course, you can write this entropy of label marginal as some kind of KL between label marginal and the uniform distribution. So it actually encourages balanced partitions or balanced classes. You can change this uniform to other priors, either learned or predicted or known a priori. So there are many variants that you can use to extend the mutual information. Okay, this is up to constant. You can use other distances or relaxation or equality constraints and so on and so forth. So you can do a lot of proxies to the mutual information. And why I'm saying this, because this is a nice, I think it's an important slide. It's not just work from our team, but pretty much a compilation of works from the community, just representative works, where in fact you can show that in areas such as deep clustering or unsupervised representation learning, especially those based on some kind of clustering losses, in unsupervised domain adaptation, in SSL. Or in few-shot learning, that they are essentially optimizing parts or proxy or generalization of the mutual information, as those I just mentioned, and it's pretty much SOTA. So mutual information regularization seems to be very useful indeed. So this is an example, transductive information maximization team for few-shot learning, which we published last year at NeurIPS. And it's very simple. So giving an embedding from base training for a given few-shot tasks, where you have labeled support sample and unlabeled query data points. So you have a cross entropy, standard supervised learning cross entropy on the labeled samples. And we take the mutual information on the unlabeled samples, as if we are clustering them subject to some supervision constraints from the labeled query samples. And we do pretty much optimize this with gradient optimization with respect just to the last layer. We fix the rest, just the last layer weights. So it's pretty much just a linear classifier giving the embedding learned from base data. So this work is perhaps a few months ago is the state of the art for few-shot learning. Maybe there are a few works that bypass this work by now, but it's very simple. No meta learning, nothing at all. You can think of it as a clustering. Okay, and it's a mutual information maximization. So the same type of losses, a little bit different, and this is interesting too because this is a transductive setting by nature. So here the task is to segment images in a few shot segmentation settings. So you have some support examples, for example, 1 image or 5 images in 5 shots, 1 image in 1 shot, and you have just 1 query image in the task, which you want to segment, basically. So, and since image segmentation is pretty much a pixel-wise classification task, then you have access to all the pixels. So it's by nature a transductive setting. So you can predict for all the pixels at the same time. And actually, in the CVPR this year, we show that it's indeed, that's all you need. All you need is to leverage the statistics of the pixels of the image and just a simple transductive inference based on some kind of mutual-like information loss on those unlabeled pixels. Actually give you state-of-the-art performance compared to very convoluted meta-learning methods, and is even much more flexible. I will show some interesting results that illustrate this. And here the difference with the mutual information is just this in regard to the label marginal parts, which is, in the case of segmentation, is just the proportion of the segmentation regions. So it's proportion of the class, basically. So we do it with respect to a prior that is predicted initially by learning. Okay, we don't assume it's a uniform distribution, of course, because in segmentation, typically the classes are not very balanced. And then we optimize this loss in the same way for each image, just last layer classifying. So this setting, or this simple methods, no meta learning whatsoever, is pretty much sought in 5 shot actually by big margin compared to very convoluted methods. 5% in meow coefficient in the 5 shot setting, 4% perhaps across different networks and architectures. So this is on Pascal VOC, the popular data sets, one of the popular data sets in semantic segmentation. Details are in the paper, but here are just a nutshell of the results that are very interesting. So there is a very interesting finding here. So we took the best methods here in the literature, meta-learning method, I believe. And what we did is, so typically methods are evaluated in 1-shot and 5-shot setting. And in meta-learning methods, there is this implicit bias to the structure of the task because we create these artificial tasks during training, during base training. So when you assume that your task is 5-shot or has 5-shot support, then you're kind of doing some kind of bias in your model or introducing some bias. And actually, and interestingly, you would observe this. So because these methods were trained in a 5-shot setting, what you observe here, and is interesting, even if you give more supervision, 10-shot, for instance, you can see a saturation in the performance. Basically, the performance is not improving even with more data that is labeled. Whereas for this simple method, transductive inference, without any meta-learning, so without any bias, then the performance keep increasing with the number of shots, and the gap keep increasing to reach 5% here, 3% in 5 shots, and maybe on par in 1 shot. So this is interesting. It means performance saturate despite the larger number of support examples. So perhaps I would be a little bit harsh here to say, well, you know, when you do meta-learning, you're kind of injecting information about what you would encounter in testing, because you're making assumption about the structure of your tasks. And this is not overfitting, but in the spirit of overfitting, because you're making assumption about what you would encounter in the testing setting. And this is what's going on here. So there is no improvement even if you give more supervision. Okay, there is even a dropping here by this state-of-the-art method. So this is it. Interestingly, also, if you have a domain shift setting in the few-shot learning setting, that is, you train your base data is based on some data sets, and your your testing data is based on a new data set. And this is interesting. This is a realistic setting. This is what you would encounter in real life, basically. And again, this very simple transductive inference has surprisingly better performance than the best performing methods. So this is it. I think before the take-home message, 1 minute I will take it for discussing this, but I just want to point to the resources that could be used about these works. So you can use all the codes are publicly available, so you could use them. They are modular. You can put them on top of any base training in the context of few-shot learning. So for Laplacian regularization, both weakly supervised segmentation and few-shot learning, or information maximization as well, both segmentation and classification. So I guess this is pretty much it. So I think my take-home message maybe is a bit harsh, but my feeling and is that there is a lot of works, but perhaps like the progress that we've seen, at least for this abundant literature based on meta-learning, might be due really to a much larger number of hyperparameter, very specialized architecture, rather than actual progress in some sense. And we see it in, when we change, when we introduce domain shifts, when we change the data sets, when we change the structure of evaluation toward more realistic setting, the performances drop significantly. And simple baselines, basically concepts from old concepts or classical concepts from clustering, from semi-supervised learning, simple regularizers, beat this by important margins. So, but of course, I mean, these do not solve the problem. By no mean we're solving the few-shot problem. For me, it is the the semi-supervised learning problem or the weakly supervised learning problem. It is the real problem. And I think the way to go forward, I think it's not about quote unquote torturing architecture or torturing training by creating complex episodes with I think there is no magic in there. It just introduce heuristics and a lot of hyperparameters and give quote unquote the illusion of progress. I think the real deal is to think of real prior knowledge, and that's complex to model. I'm not saying it's easy, it's in a nutshell, but real prior knowledge and real context to embed and to drive these models depending on the task. I always talk about radiologists and medical doctors. I mean, they spend years and years in their training. So I don't think they're, for example, it's an insult to tell them, guys, we're gonna solve this with CNN, your problem. You spent 10 years of your life or 15 years training and reading, a medicine textbook and anatomy textbook and so on and so forth. So I think we should be humble as a technical community, and I think, yeah, it's a very difficult task to embed prior knowledge, but I believe that's the way to go. And by no means these simple regularizers are solving the problem. They are just uncovering that we are going into the wrong direction, I think, in my opinion. So this is pretty much it, and I think we'll have some time for a few questions, if any.
Thank you. It was excellent. Could you contrast this with, or can you describe how this relates to active learning or budgeted learning?
Well, I think it's very highly related in so you can think of active learning as some kind of targeted semi-supervised learning, or where you try to choose the best new samples in your unlabeled data, and there are even actually active learning approach literally based on clustering. So you cluster your data and you try to choose the next sample in a way that maximize diversity in your data, or in a way that those new samples are the most difficult ones. So this is obviously highly related.
But thank you.
So how does it relate to sort of data augmentation? Data augmentation is what is typically used to generate, examples. Also, there are, domain adaptation techniques applied to data segmentation as well, using generative adversarial networks and so on.
Yeah.
So what do you think sort of the drawbacks of applying say, data augmentation technique as opposed to few-shot methods?
So data augmentation techniques are somehow, at least, let's say, if I think of them from the perspective of what's being done now in unsupervised learning, contrastive learning, are some kind of data augmentation technique. So you are kind of injecting prior knowledge in the sense that your tasks should be invariant with respect to rotation scaling because you're dealing with images and scenes. So, and then what people do in contrastive learning, for instance, you augment your data or you transform your data, which they call view, and then you embed losses that make sure that the predictions are consistent over these different views of your data. That is some kind of data augmentation. And data augmentation is highly related to everything that I mentioned here, because at the end of the day, if you do it on unlabeled data points, that is contrastive learning, you are pretty much injecting priors about the invariance of your data. Does it make sense a little bit?
Yes, good.
You're augmenting your data, yes, but you're injecting priors about the invariance. You're not augmenting in some random way. You're not making your pixels just go crazy and not representative of the world. You're doing rotation, translation, and scaling. Those are priors about the task. And the other question was domain adaptation. Yeah, maybe I could come back. Yes, indeed. Domain adaptation was, it's pretty much in the same line of what I was mentioning about meta-learning, was dealt with tons of work with adversarial neural networks, which are also Pandora box of hyperparameters. And again, I put it here actually, unsupervised domain adaptation. So the state of the art, one or two papers last year and this year, are actually exactly doing something very similar to the mutual information, without adversarial networks, without complexity, and they are pretty much reporting quite very competitive performances. It's highly related, and you don't need these. In fact, at least from those papers that are, from what I see, quite reproducible, and they are highly related. So I can give the full references if you want.
Okay, great. Thank you.
So you can ask for the slides. I shared them.
There's a question posed in the chat.
Questions posted in the chat. Okay.
How to do
few shot learning for open set domain adaptation and continual learning tasks?
I mean, yeah, interesting. I haven't thought about it. I wouldn't answer in 30 seconds, but well, it's interesting. Actually, this is in line of what I just mentioning. The current few shot benchmarks are very simplistic. They are not open set. They don't assume domain shift. They assume fixed tasks in terms of support samples and so on and so forth. So it's very simplistic. We have to move toward more realistic assumptions. More realistic assumptions means no assumptions. You make it open set, you make it domain shift, you make it whatever, name it. So all this is interesting research line to move forward. So instead of competing over 1% over year on a data set that is not realistic at the first place, because we are tuning hyperparameters and adding hyperparameters and adding complexity and torturing gradient, quote unquote. I mean, I think it's better that we start opening to very challenging tasks, like, for example, few shot learning with an open set. I think that's the way to go. How to do it? I don't know. Like I said, we by no means we are saying we solved the problem. I think we are barely touching the surface and starting. I think we're just setting baselines. And saying, okay, let's take a step back.
Maybe if I ask one final question. When you're doing like one shot or 5 shot learning, what is the variance? I'm assuming if you get really relevant things, again, think of active learning that really lets the learner focus on things which he considers important. I could imagine there's certain pictures of cats that are really informative, the ones which don't really help that much. Did you get a high variance as you tried different individual images to be included, or different individual instances?
Well, I guess the way we evaluate this is we generate thousands and thousands of tasks. So we take ImageNet or mini ImageNet and we start generating tasks, sampling randomly, for example, 5 classes. per task, and each class is 5-way or 1-way, 5-way. So 5 classes, and each class is represented by five example, for instance. So there is some kind of diversity across tasks. So this is the way we evaluate it. There are also, though these are the standard data sets, there are also data sets that are getting more and more complicated, like the metadata sets, where the number of support samples and the number of classes and the sampling start to get more complex and more random. We're going into the right direction, I would say, in that sense. Does this answer the question?
I was wondering whether I could imagine, again, thinking again about active learning, I could imagine where if I give you, a few examples, if they're right by the decision boundary, that does a lot of, that gives information when they're labeled. If they're way over there.
Oh, okay, I see. So, okay. So the question is, if you, why not choose the few shot? Well, yeah, of course. Yeah, interesting.
Well, how variable was it? I mean, maybe I'm wrong. Maybe my intuitions are wrong. If you take 5 examples at random, chances are you're going to do a really good thing. But I can also imagine some sets of 5 examples do really good jobs and really badly. That's why I asked about the variance. Did you get a sense that if I chose, if I choose a domain, choose random pick 5 examples and look at the classification accuracy and do this 100 times, is it always 82.1% plus or minus 1%, or is it between 51 and 89% accuracy, depending on which set of 5 examples you chose?
So you mean the choice of the 5 example might
Yes.
make a big difference. But this is why when we evaluate this, we really sample randomly and we create a big number of tasks.
Yeah, and what was the variance?
But the variance, yeah, I don't know whether we report the variance. That's a good point, actually.
Well, I was looking for your slides. I didn't see it. That's why I was wondering whether, I can. The point is, I might be wrong. My intuition is some sets of 5 would do really well and some would do really badly. But maybe I'm wrong. Maybe just 5 at random. There's a 95% chance you get really good ones because of the way the space is structured. I could also I'm just curious about what that looked like.
I see your point, but I guess the creating random tasks is what kind of answer this, right? Am I wrong? Maybe I didn't get fully the question.
Well, just if you just, that's okay. It was just the general issue of again, the active learning community says it's important to choose the right examples.
I agree.
And this approach says, that doesn't matter. Just choose 5 examples at random. And I was just wondering whether the active learning community has focused on examples where the detailed examples makes a difference, or whether in fact this is misguided, that in fact you get pretty good if you do 5 examples, just pick them at random and you'll do about as well as any other 5 you picked. And so
well, I guess they are not like the few shot and the active, they are not mutually exclusive or in contradiction. I mean, I think the few shot are just didn't realize that it's interesting maybe to build tasks in an active way, in an active learning way. I think this is interesting. They are just so much focused on learning from few examples and evaluating
which examples, and maybe it doesn't matter, or maybe it does. The active learning community says it makes a difference which one you choose. This few shot learning says, choose whatever you want.
Or maybe the few shot learning, they assume you are in a setting where you just have n labeled example. That's it. You don't have to choose among millions example to choose 5 among million, but you just have those 5, maybe. But I agree that it's interesting to merge actually both and choose tasks based on an active learning.
Just a thought again. I have some experience with active learning and no experience with few shot learning aside from that. So
well, I haven't seen an active few shot setting, but
well, most active learning is few shot, right? I actually has a small.
Yes.
The learner gets to say, I want that one and that one. Oh, now that I want that one. I
mean, it's very interesting. It's very interesting because I know that people are working actively into generating more realistic tasks in few shot learning. That is, the number of support change, the structure of the task change, and so on. We start to see work like the metadata set that just appeared last year, a big one with a lot of dimensions. But I think generating tasks in an active way is an interesting, in an active learning is an interesting research avenue. I've never thought about it.
Great. Great talk. Thank you very much. There's more questions.
There is one more question. What is your opinion on visual transformers for semi-supervised or unsupervised learning?
Transformers? I think I don't have an opinion about transformers for the simple. I don't want to make opinion if I'm not familiar with the subject yet. Perhaps I still did not get enough motivation to look into transformer very carefully. Is it gonna be helpful? Perhaps, I don't know. Like transformer versus CNN. For me, are architectures the most important part? I don't know. Perhaps transformers will have some good inductive biases that will help generalization better. I'm very uncomfortable talking about something that I do not know exactly. I know it's gaining in popularity, but from what I saw, for instance, very quickly, I don't want to make any claims, but from what I saw, for example, in some segmentation networks, I'm not completely convinced that, like it seems like even the performance reported are kind of in favor of transformer in some sense. That is, we kind of degrade a little bit the baselines that are based on CNN. There is a push from the community, obviously, to make them look better. I still did not see evidence, at least on my superficial level, I still did not, that this is going to be super helpful, but I hope so. Why not? By all means, if it has some good inductive biases that are helpful for tasks like in vision. So I'm not the person to answer this at this point. I mean, I didn't get there to transformer yet. I'm a bit slow to catch up, but so I don't really know. So those results were mostly based on CNNs and ResNets and standard networks.
Great. If anyone has questions, please feel free to unmute yourself and ask Ismail directly. If not, then let's thank Ismail for a wonderful presentation. And we have, I think Ismail has time for one-on-one meetings, and the link for that is shared through the email, but I'll post it in the chat box once again, so that everyone, if someone wants to have a one-on-one meeting with Ismail, you should join through this Google Meet link.
So I can go and connect on the same one now.
Yep. Yes. So, sure. Thank you, Ismail. Have a great day, everyone.
Okay. Bye now.
Bye-bye.